Hey everybody. So today I want to talk about this blog article, and it's not a blog article, or not a research paper, it's a blog article, Defeating Non-Determinism in LLM Inference, and then it's put out by Mariam Mariotti's company, Thinking Machine Labs. So I've held off my thoughts on this particular paper for a few weeks now, just because I didn't feel that it was worthy overall of diving deep into my thoughts on this research paper, but I see more and more people because of this research, of this blog article very specifically, diving deeper into this research, right? And then trying to defeat non-determinism and LLM inference. And then so, overall, to me, I'll state my blanket claim and statement within this, that the research within that is not possible within the realm of physics. That's just the bottom line of how it breaks down. You will never be able to eliminate determinism from AI models because they work on probability inherently, and there's probability in both the hardware and the software and the mathematics, right? It's just there's literally no way to get rid of that. Why would you listen to me and on these things as opposed to Mariam Mariotti, right? Which is why it's hard to talk about this overall. And then so to me, I have very specifically an NDA around this topic overall, but I have a lot of extensive research that I've dove into. What I can say is that I've worked very extensively with vectorization and determinism of vectors, and vector computing within this particular instance, right? And then vectors solve and trying to create deterministic vectors solve a lot of the problems that get around, and also face a lot of the problems that I talk about within this, right? And then, but so you haven't heard anything about anything around that at all. So that kind of tells you what the success was of that overall, right? And then it's all physics problems. So let's dive into the physics of this, right? And then so first of all, the paper very specifically deals with non-determinism, and then so what causes non-determinism according to the blog article very specifically. So they reject the usual floating point plus concurrency explanation as insufficient. And then this is the important word here, right? Insufficient. They don't say that it's not true. They say that it's insufficient to overall in order to prove determinism, which is important, and I'll touch on this in a second. But so while floating point non-associativity, for example, A plus B plus C is not equivalent to A plus B plus C, is real and matters it alone does not explain when outputs differ under same prompt, same model, same temperature equals 0. And then so within this, what they're saying is that this equation is a true equation, that this does, but this does occur, that this non-concurrency occurs. But they say that essentially this is a smaller part of the problem, and then a larger part of the problem, this is what the blog article says, is this, right? Lack of batch invariance. And then so within this, in inference pipelines, requests are often handled in batches for efficiency. So the same prompt processed alone versus processed as part of a larger batch can get different numerical behaviors, especially in kernels like matrix multiplication, attention, normalization, because batch shape affects how operations are scheduled, how reductions over parallel threads are done, and so on. Even though individual kernels may be run to run deterministic for a fixed batch and fixed hardware software stack, the way they behave under different batch sizes or when requests are grouped can lead to a subtle numerical differences that cascade through the network and eventually yield different final outputs. So the problem with I think my problem with this, and a lot of people's problem, I think, as far as what I've seen people talking about within this, is that none of this is untrue, right? So every statement within this is true. Yes, this is all true. This is exactly what occurs, and then but the problem is that there's other areas where probability gets introduced far beyond just this problem, right? They're saying that essentially, rather than like this whole entire pie of problems causing this issue, they're narrowing it very specifically to batch invariance, and like if they fix the batch invariant kernels is what they introduce, then they'll solve that. But that's solving again like just a slice of the pie, right? And then they don't even solve fully that slice of the pie, and I'll dive deeper into this, right? So what they did and what they proposed. So they recommend and provide batch invariant kernels, or versions of computational kernels, which are designed to produce consistent numerical results regardless of batch size or request groupings. They give guidance on how to enforce the fixed reduction orders, avoid adaptive splits and attention based on cache or sequence links, etc. And then they support this with experiments that they've run. And then they use batch invariance kernels. They got bitwise identical results for those repeated prompts under their test conditions. So same exact hardware, same exact software, same exact prompt settings, same exact prompt. So, for example, reproducible inference in these specific tests. And that's the important part of this, right? So, and there's a few elements of this to highlight. First of all, they're setting temperature to 0. And then second within that is that like they're utilizing literally, I mean, it's same hardware, same software, same prompt settings, same exact GPU, the same exact CUDA kernels, everything, right? Like everything has to be identical. And then once you go through a CUDA kernel update, etc., anything along those lines also introduces probability within this mix. But also too, when the CUDA kernels themselves, right? These kernels, when they're performing these calculations, they don't always compute this, exactly going back up here, right? They say they don't disprove this. Like they say that this is like they say that this is just a small problem, but this is this is a rather large problem, right? Because this means that you can never get determinism as long as this is true within it, like which has been the argument from the beginning of this, right? Of computers and AI when it comes to these, because when the computers are calculating massive matrix multiplication tables, they don't always compute the numbers in the same order, in the same sequence, same hardware, etc. Like there's literally anything can throw a variable into it, right? Which is the important thing to highlight within this. And then so you can smooth those variables, and then smoothing those variables is good. Like there's nothing bad about smoothing those variables. Well, there is, right? And then so we'll get into that, right? Because so there are limitations and costs to this. The very first thing is that there is 1,000,000% a performance cost to doing this. So these kernel modifications that they do within this are they essentially incur overhead, right? And then the deterministic batch invariant version is slower than optimized non-invariant kernels. And then so it's just you're like nothing that you can do about this. There's more mathematical overhead, so it will always be slower, require more GPU, etc. They did this, and this is, I can't highlight this enough, right? They did this in the most controlled environment possible. So their reproducibility is demonstrated under settings they control like to a T, specific hardware, software versions, kernels, environment. If you change those, then it may break. Like it could literally be running it in you ran it in your lab in San Francisco versus they ran it in their lab in San Diego, and there was like the temperature in the room had a variance within it that would cause environmental conditions enough to create measurable differences within this, right? So it's important to highlight that you need a science lab, and every piece of every system has to be identical. And so they do not claim to solve all sources of non-determinism, and that's the important part of within this again, right? So they don't claim to solve for determinism and model updates, API changes, hardware changes, non-zero temperature sampling, etc. in production settings. These are outside of the scope of all of their experiments so far, right? And then like where they're trying to get money is to investigate into this further. And so realistic possibilities versus what's a dream within this. So here's like an exact side-by-side of what seems achievable based on their work versus what remains or seems extremely unlikely in current real-world AI deployments. And then so as far as what's realistic and plausible, it's reproducible outputs for identical prompts under controlled inference settings. So you're setting the temperature to 0. You have fixed hardware, fixed software, fixed batch shape, because that's what they've demonstrated, right? But so what's a pipe dream is always identical outputs, and then like across hardware, driver versions, after updates, once you change the GPU, the CUDA kernel versions, or even batch scheduling, things that can drift. They haven't shown that it works everywhere, right? Like they haven't solved all of the problems, and then so if you have any of these variables that come into play, which like in any real world setting, you're gonna have any of these come into play, right? Reducing variance caused by how prompts are batched. So, for example, when server loads, requests, grouping, etc., this seems fixable, and their batch invariance kernels are a practical mitigation. And then so like this is the important concept to talk about within this, right? That they reduce variance, and then so reducing variance within these models is already known, right? Like, and that's 100% in the realm of physics. Like, and it's like easy to do, right? Like, and so I can tell you up front that you can reduce the amount of probability and the amount of non-determinism in these models, but you can never bring it to 0. And that's just how the physics and the mathematics work within it, right? And then simplistically, like the further that you shrink that variance, the less performant the model actually becomes, right? The less generalizable the model is, and that's the trade-off, and that's a mathematical and a physics-based trade-off. So what they can't do within that is eliminate all sources of non-determinism. Like they just flat out can't do it, including floating point hardware quirks, internal caching, external pre-post processing, tokenization differences, etc. Right? That seems infeasible in any setting. Basically, like they can't do it in any real-world setting. So what they can do is use use their framework within systems where reproducibility is critical. So research, evaluation, testing, benchmarks, debugging, scientific studies. These systems can accept latency cost or restrict environment and have version control, right? Like if you want to utilize AI in these types of settings, this is going to be more deterministic than deterministic models, but like the defeating non-determinism is like it's a pure marketing play, and you'll never be able to do it, right? And it's so like what you won't be able to do is make every API call from every user forever reproducible. And this is like this goes to AI agents too, right? Like it's been 3 years now people debate these things, and so regardless of server load, batch shape, back-end updates, etc., especially in public services where performance, latency, throughput, and cost are key. The bottom line is that even in like an API call, very specifically, like you're inputting variables every single time that the API call is executed, right? It's just you're introducing mathematical variables, and then so what they can do is have acceptable performance trade-offs, and then the performance trade-offs are built in, right? So for certain use cases, for example, when you don't need ultra low latency, or you can restrict request batching, for those instances, you might use batch invariant inference. So in instances where you can sacrifice GPU cost and speed for the general, like you very much want to squeeze out every single part of accuracy that you can get out of the models. And then so what you won't be able to do within that is produce deterministic behavior with no performance penalty. So you'll get no constraints. You won't get no constraints or no trade-offs. That would be amazing, but so far, batch invariance slows things down and constrains how the kernels are operated. You will get engineering reproducibility. So versioning, software, drivers, hardware, kernels, testing with fixed prompts, ensuring deterministic inference pipelines. These are doable and beneficial, right? So like again, like it's the more that you control the inputs, the more controlled the outputs are. And then this is just another method towards controlling the outputs, which is never bad overall, right? Like that's the big thing within this. Like nothing within this is a like bad that it exists. It's just like it's not ever going to be a you're never going to defeat non-determinism. And then so what you won't be able to do is guarantees of deterministic AI in marketing. Like that's like, to me, that's what they do within that's my problem with this, right? Because this is in marketing terms a guarantee of deterministic AI. That's what they're playing off of within this research paper, and they're playing off of your ignorance of these things. Within that, they're not making the claim, right? That's just the title of the paper, and in the blog article. And the blog article, they very specifically say these things in the blog article, but like it's like hard for the average person to break it down into these terms, right? So, what you won't be able to do is, so again, you can't guarantee deterministic AI in any marketing, and that would imply always same outputs in any situation, which glosses over constraints, and it's purely misleading. So why these claims feel like hype, right? I want to try to break this down for the average user. And then so there's three things that you need to look at and pay attention to and understand within this. The first concept is hidden dependencies. Even if you make your kernel batch invariant, if your GPU driver or math backend library changes, so you have CUDA kernel updates, the numerical behavior can shift. So reproducibility depends on controlling everything, right? So this is every hardware, software, and math, you have to control every single, and drivers, you have to control every single variable, right? Also, too, you need to set the temperature of the model to non-zero, and you need to set sampling to 0, so no Monte Carlo. And then so many real-world uses don't use pure greedy decoding. They sample using top K, nucleus sampling, etc., which introduces randomness by design. Like you're introducing sampling in and of itself, which you generally want to increase model performance, introduces more probability to the model rather than less. And then so within that, if you're getting rid of this, you're inherently sacrificing performance and sacrificing the maximum performance of the model that you could get up front just to make it more deterministic. You can turn the dial, right? And that's what you're doing. You're turning the dial. So you're sacrificing this because this is towards the top of the dial, and then you're moving away towards the opposite side. And then context matters, right? So the prompt context matters, the tokenization matters, the hidden state matters, the caching matters, the memory writing to memory. How exactly if you have two different memory modules, right? These can all have subtle effects that differ depending on how the model is deployed. If prior messages or preceding system messages differ even ever so slightly, or if internal caching changes, outcomes might still vary. You also have cost and latency trade-offs. So ensuring batch invariance can make inference slower, less optimized for throughput. Overall, that's just repeating on the top, right? And then you 100%. So within all these things, what these things break down to is a drift over time, which they don't solve for, they don't claim to solve for, and there's no way that they can solve for in a real-world situation, right? So in real-world terms, models get updated, infrastructure changes, libraries are optimized, hardware evolves. Ensuring determinism in one deployment doesn't guarantee determinism once any of those factors change overall. And then so what they have done within this, right? So they found that one big reason you sometimes get different answers from the same AI, even when it's supposed to be predictable, is how the system batches up requests. When the AI handles several prompts together versus one by one, the math inside, especially the floating point additions and normalization, ends up happening in slightly different orders. And then so that batch, think of it like a batch of packages coming off of an assembly line into a truck, right? And then those, if they're just falling off of a assembly onto a belt, if they fall off, they could fall off in slightly different orders, right? And then those tiny differences of just those boxes falling off in a different sequence every time you do it can blow up through large networks, because you're talking about these billions of conveyor belts, right? And then so through large networks that can change the final answer when you have that occur over billions of conveyor belts. And then so they built improved math kernels, which are the inference components that don't change behavior depending on the batch size. And then so with that, in tests, they got identical answers for repeated runs on the same prompt under the exact same controlled conditions. And then this is like controlled conditions is the important part within an element within this, right? And then so what they haven't done and what they can't do so far, at least. So they have not made public a system that is guaranteed deterministic in all circumstances. So different hardware, server loads, API versions, etc. They haven't solved the randomness or drift that comes from non-greedy decoding or sampling temp strategies. So turning temperature to 0 or utilizing sampling whatsoever. They can't guarantee the same behavior if you update kernels, drivers, or you change how the AI is deployed. So like a different GPU, anything at all different with the environment. There's a performance cost to the level of determinism that they demonstrate. For many applications, this trade-off will matter. And then because you'll need the performance, but you won't be able to get the performance because you'll need to sacrifice it for accuracy. So realistic takeaway for everyday users or developers: if you care about consistency, for example, testing, research, or reliability in regulated environments, this work is important. You can expect AI outputs to become much more repeatable under stricter conditions. If you build on this, you can start writing systems where same prompt equals same answer is true more often than not. But that's the end that you'll ever be able to get to this, right? It will always be true more often than not, and you will never be able to get past this roadblock here. So if someone tells you that their AI is now fully deterministic, always, everywhere, under any conditions, you should assume that's marketing. The always part is where the promise breaks down. The bottom line is that Thinking Machines Labs works in a solid step forward. They've identified a non-obvious source of inconsistency, shown it can be remedied under certain conditions, and produced prototypes and kernels that enforce reproducibility in those settings. However, solving determinism as a blanket, meaning same output for same input no matter what with zero losses, remains out of reach, and at least for now, but it's out of reach, right? They are not defeating non-determinism in LLM inference. There are always environmental, hardware, architectural, or decoding strategy factors outside of their claim solution. And then so let's kind of like dive deeper into that, right? Why a 100% fully deterministic AI model is impossible. So let's break this down fully, right? So what exactly deterministic means? A deterministic system has the same input always produces the exact same output. So as an example, a calculator is deterministic. If you put in 2 plus 2 into a calculator, it's always going to output 4. And you know that the calculator will produce. If the calculator doesn't produce 4, the calculator is broken. AI companies sometimes claim that they've made deterministic AI, but a 100% fully deterministic AI model can't exist. Not because of sloppy engineering, but because of the laws of physics, literally. So computers are built on imperfect numbers. Modern AI models run on floating point arithmetic. These are approximations of real numbers stored in computers' memories. This is how all of them work, which is why you get to this. So this is the result of a floating point equation, right? Because of the laws of arithmetic and floating point equations, you get this, what we're looking at here, right? And then so that tiny mismatch is dictated by how electrons store and move numbers. You can't fix it. It's baked into the physics plus the computer design. This is just inherently true, right? So the result is that even if you freeze an AI model, you get tiny round-off errors that sneak in because of this. So parallelism creates random order. AI runs on GPUs with thousands of cores working at once. They don't add things in a fixed order. the order depends on how the hardware schedules work in parallel. Physics says the timing of the electrons, the heat fluctuations, and even like microscopic noise mean that you can't guarantee identical ordering every single run. Like any of these conditions mean that you don't have identical conditions. And then so the result is that the math unfolds in slightly different ways each time, even with the same input. So this leads to hardware and environment shifts. So two identical GPUs, even if it's like the same manufacturer, one was produced right after the other. They're not guaranteed to have the exact same behavior. There could be microscopic differences in the manufacturing and thermal noise that make them diverge. And then also too, on top of that, what would make them diverge is drivers, libraries, and compilers, and then those also change how instructions get executed. If you're on Python version 3.24 and then you run it on Python version 3.25, it could be a difference, like just flat out how it is. And then so the result is that you can have the same AI model on two different machines, and you can't be guaranteed to match bit for bit forever. AI is probabilistic by nature, and this is just the most important element of it, right? LLMs don't store facts like a database. They predict the next word based on probabilities. The big thing, I'll go through this. And so even when you turn randomness off, you turn the temperature to 0, there's this ties and hidden rounding differences make outcomes diverge, right? Setting temperature to 0 does not mean that the models become deterministic, which is why there's introducing their paper claiming to solve for non-determinism. Even if you removed all probabilities, you'd kill what makes an AI intelligent, like what it does, right? It would stop being generative and it would just act like a calculator. And then so the result of this is that full determinism means that there's no intelligence left at all. It's full determinism is a calculator, right? That's exactly how it works and what that breaks down into within this. And then so within that, and tying this into I think a larger thing that I've noticed as to how it seems to me people break down AI in their minds. People are like, why don't you just write this rule into the model, make it a rule that the model does this, right? Because the model doesn't operate off of rules. There's no rules programmed into these LLM models. There's no the 3 rules don't even exist for the models, right? Because there aren't rules. It's not how the models work overall. Their rules are based off of the math, right? And algebra. They work off of algebraic rules. And then from that they learn to predict the next word based on probabilities, and that's what they do and store within them. And then so next concept within that is that physics doesn't do perfect repeatability. So at the deepest level, physics itself isn't deterministic, right? Because you have quantum mechanics, which introduces unavoidable uncertainty within itself. And then because you're dealing with, at this point, at the factors that matter to these things are electrons, the temperatures, etc., right? And then so you're literally breaking it down into the quantum level, and then so the quantum mechanics of those things matter, right? And then because you can't control the direction, the full probability of an electron itself because of quantum mechanics, then you have some sort of variability and probability that will always be introduced at that level, right? And then you have thermal noise. So thermal noise jiggles transistors inside of your chip. Again, these are just things that you are fully outside of your control. And then electromagnetic inference can create tiny unfixable differences. And then so if the sun has a sunburst or doesn't have a sunburst during the time of your experiments, or it's winter as opposed to summer, or you're in North America as opposed to Australia, literally anything, there's so many variables again. So these aren't bugs, they're fundamental features of how the universe works overall, right? So what is possible. So we can get variance reduction, making AI outputs more stable. And then, so again, it's like a dial, right? And you can turn the dial, and we know how to turn the dial. And then, so this is useful, and this is another tool for turning the dial, but you will never be able to turn the dial to off. Reproducibility under constraints, utilizing the same hardware, same software, same setup, same decoding equals often reproducible. And then, so that's what you get. Like, if you do all of these steps, the end result that you get out of that is often reproducible, and you won't be able to get it higher than that. You'll also be able to get auditability, so tracking uncertainty, so you know how reliable the answer is, but 100% determinism across all environments forever, not possible under physics. Bottom line, whenever someone promises a fully deterministic AI, translate that to we've reduced the wiggle, but the dice still roll underneath. And if they claim more than that, it's marketing hype and not science, just pure bottom line. Like, you can dismiss it as marketing hype at that point immediately. The laws of physics guarantee that AI can never be 100% deterministic, just more or less predictable, depending on how much stability you're willing to trade for speed, cost, and usefulness. And I'll leave a link to this document here. If you like this type of content, please like and subscribe. Thank you very much.